Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be focusing on coordination compounds. So we already know that metals tend to give up their electrons to nonmetals and make ionic species. However, we also know that these positives and negatives tend to attract. And so previously we've looked at how we can take these cations and anions and form solids. However, it turns out a lot of these will form actual complexes that can actually hold together in water and not just dissolve into their constituent ions. These more complex ionic species are called, well, not surprisingly, complex ions because us chemists are so clever at naming these things. And we've already seen a couple of these. One noticeable example is going to be aluminum hydroxide, which we've made in lab. So in this case, we have a central aluminum atom bound to more than one group called, in this case, hydroxides. So this aluminum center, now since it's bound to 4 hydroxides, each of these hydroxides has a negative charge. And even if the aluminum starts with a 3+ charge, this gives the overall complex a negative charge. Now, the interesting things about this is because you have an overall charge, it means that it doesn't readily form a solid. And if it does, it needs some sort of counter ion like sodium or potassium to cancel out that negative charge. You put too many negative charges in a place and it ends fairly badly. As a result, because it has this overall charge, it means that it dissolves in water fairly well, because water loves a big dispersed negative charge like we have in so many of these complex ionic systems. And these various complex ions, where you have a metal and something bound to it, is called a coordination compound. And coordination compounds actually encompass a wide variety of species, but they're essentially broken down into two key constituents that we have here in our aluminum hydroxide species. The first is going to be some sort of metal center. Often this is a transition metal. So again, think about your D block elements. But as illustrated here, you often have some of these main group metals like aluminum, tin, lead, bismuth, which also like to get in on the action. And all of these share a very common feature. They are Lewis acids, meaning they have very few electrons because normally they have a positive charge. Is a good clue that something wants more electrons, or is a Lewis acid, is if it has a positive charge. On the other hand, we have ligands, and these tend to be electron-rich compounds. And as a result, since they're so electron-rich, they tend to act as Lewis bases, so they have electrons to give. The metal has electrons to help stabilize itself. But as we've seen, most of these Lewis bases want to hold on to at least some of their electrons, and most of these Lewis acids can't hold on to a full electron pair, so they need to make some kind of arrangement. So for example, when we're looking at this aluminum hydroxide, we have these 4 hydroxide groups, each with a negative charge, which can reach out and coordinate to the aluminum. So again, here the hydroxide is acting as a Lewis base, the aluminum is acting as a Lewis acid, and we have this overall complex, which again, that negative charge helps stabilize the positive and vice versa, making everybody happier in the end. However, it turns out this doesn't just have to happen with negatively charged ligands. It can also happen with neutral ligands. And a good example here is ammonia. And we know that ammonia acts as a base because it has a pKb of about 5, which means it's a fairly strong base, meaning these electrons really want to be somewhere else. So they can reach out and grab a proton from solution, or they can go find something like platinum with its nice +2 charge, reach out and grab that platinum center. And this gives this overall complex that +2 charge, where again, the amine is acting as a Lewis base and platinum is acting as a Lewis acid. And we see this with the formation of almost all of these coordination compounds. Lewis acid, Lewis base. And again, as a general rule, just like we saw with acid-base reactions, our bases tend to be negatively charged because those are the species with extra electrons. But some of these will be neutral, most notably nitrogen-rich compounds. So if you see a nitrogen species that isn't surrounded by 4 different groups, be aware that it will often reach out and grab a metal because that makes everybody happy. And again, one of the good ways to look at this coordination event is sometimes we can imagine these as being full ionic species, where we have a negative and a positive charge holding the species together. But sometimes these electronegativities of our constituent atoms can be fairly close. So it's not quite a full ionic bond, but it's more polar than a polar bond. So a lot of these coordination events really happen right on that spectrum of whether it's ionic or polar. But as a result, it's going to be really these charge differentials that help hold everybody together. So when we're looking at these coordination events, one of the things we can keep an eye out for is how differently we can arrange all of our ligands around our metal center. And these tend to happen in one of four key ways. So either if we have two ligands, we tend to form a nice linear complex. This is very common for metal centers that have a single positive charge. However, as the charge and the size of the system gets bigger, it's much more often that we will end up adopting four different ligands. However, due to the nuance of the position of the atomic orbitals around the metal center, these can either be arranged as a square planar structure, such as in platinum, or as a tetrahedral structure, such as zinc. And this is often due to the location of excess electrons, which are in lone pair-like locations, which we won't get into here. And so usually you'll have to be informed of whether a structure will adopt a square planar geometry or a tetrahedral geometry. But as a general rule, if an element tends to adopt a square planar geometry with one set of ligands, it often will adopt that geometry in general. However, one of the most common and most defining types of geometries for most of our metal coordination compounds is going to be the octahedral geometry. Since we're dealing exclusively with metals, which tend to have those d orbitals, they're able to do this much more complex bonding geometry where they can bond 6 different ligands at once. And the exact number of ligands and the exact arrangement is often controlled by the identity of the metal, but can often be controlled by the charge as well. For example, platinum tends to like to adopt a coordination of 4 different ligands in a square planar geometry, whereas if the charge goes from 2+ to 4+, it starts to coordinate 6 different ligands in an octahedral geometry. As a result, platinum is very expensive because it is used in all kinds of different chemical reactions and is a key component of the catalytic converter in your car, which helps reduce emissions. And we see several different atoms with specific charge states that can do these kind of conversions, such as aluminum, which can coordinate either 4 or 6 molecules, but again, often in this case, a tetrahedral or octahedral state. But when you're trying to imagine the structure of a molecule, you're often going to be adopting one of these 4 major types of systems. That gives us an idea of what the metal looks like. However, it's often very important to know what the ligand looks like. So for example, here is a nice cobalt complex that's actually fairly similar to one that we synthesized in the lab. They can actually coordinate 6 different ligands. And you'll notice that each of these ligands is attached via a single point. We have a single bond in between our ligand and our metal center. Whenever this happens, this is called a monodentate ligand. It's bound one time. And it turns out most of the ligands you will encounter will be these monodentate centers. And they're very similar to a lot of the structures we've seen before, and includes a lot of very familiar molecules, including water, which can bond through an oxygen because that's where the lone pairs are, amines, carbonyls, nitrogen oxide, as well as much more complex species such as nitrite groups, which can either bond through the nitrogen or the oxygen, as both sides have lots of electrons. However, if it bonds through the N, we tend to denote it with an N, and if it binds through an oxygen, we tend to denote it with an oxygen. So there is a wide array of ligands which have a lot of electrons on one single location, which can reach out and hold on to that metal and just doesn't let go. However, there's a lot more complex ligands which may be able to bind through more than one site. So a good way to look at this is they contain more than one Lewis base. And if they bind through two or more sites simultaneously, these are called polydentate ligands because they bind, dentate, through more than one spot. So they bite in multiple locations. So for example, one common species here is ethylene diamine, which we've seen before with acid-base behavior. It loves to bind to metals because these two different nitrogens are far enough away that they can both grab onto a metal simultaneously. And we have three major polydentate ligands that we work with: ethylene diamine, oxalate, and ethylene diamine tetraacetic acid. And let's go ahead and look at these three since they're very common in a lot of real uses. So the two of the most common ligands are going to be ethylene diamine and oxalate. Note that these are common enough that they get a nice little shorthand notation: En for ethylene diamine and OX for oxalate. However, do note that in order to be an adequate enough Lewis base to bind to a metal, oxalate will have a -2 charge. In other words, it will be fully deprotonated. Again, just like ethylene diamine, the difference is ethylene diamine will be neutral when it's fully deprotonated, and oxalate bears a negative charge. Now, both of these ligands bind through two different centers. In oxalate, it binds through two different oxygen atoms, and ethylene diamine through two different nitrogen atoms. If you have two different binding centers, this is called a bidentate, two-centered, two bites. And these can reach around and grab metals, forming nice and very stable rings. So for example, looking at ethylene diamine, both those nitrogen atoms can reach out and coordinate to the platinum, making a nice 5-membered ring. And one of the features you'll find that occurs a lot as you move on to organic chemistry is that rings tend to be very stable. And so as a result, these polydentate ligands tend to be very favorable coordinations to metals and are very good at binding them up and removing them from circulation, which is a topic that we'll look at over the next several lectures. So whenever you have any complex that contains these coordination rings, they are called chelates. So in this case, you can say that platinum has been chelated. It's been bound into this rather stable and less active ring. Any of the ligands that form such a complex, such as ethylene diamine or oxalate, are chelating agents. And these happen a lot in nature. And in industry. Ethylene diamine is often used in a lot of catalysts, and oxalate is often used in your body to bind up extra metal. This can occasionally be catastrophic if you build up kidney stones, where you have a lot of oxalate that's bound up to extra ions, such as calcium in your body, making a stone that is rather hard for your body to get rid of. However, the granddaddy of coordination compounds is called ethylene diamine tetraacetic acid. That is a mouthful, but we can kind of break it down into parts. In this center group, you see an ethylene diamine, two nitrogens bound together by an ethyl group. So that's where the ethylene diamine happens. And this is going to be a fairly good coordination group. Again, it is a bidentate ligand. However, because this isn't enough, we threw on 4 different fully deprotonated tetraacetic acids, or acetates. And this whole complex collectively is known as EDTA, ethylene diamine tetraacetic acid. And it is really good at its job, because what EDTA can do is we saw that a lot of metals can have 6 coordination sites. EDTA is one of the very small set of molecules that can wrap around all 6 of those sites. And it has enough selectivity that it can do so to a astonishingly wide range of different metal ions. So no matter what the metal ion is, if you have too much of it in solution, you can throw in EDTA, and as long as it's been fully deprotonated, so you've removed all 6 of the various protons that can coordinate to EDTA, you can, congratulations, form this very reactive binding complex. And it's worth noting that EDTA is so effective at its job that it shows up in astonishingly range of products. So it's used for a wide range of things, like binding up toxic metals in things like pollution, toxic spill sites, because it's very good at binding things like lead and mercury. So if you need to remove them from the system, you go ahead and throw in EDTA just to be safe. However, if you go ahead and grab a can of Coke off the shelf, because Coca-Cola doesn't want their soda to taste metallic, it throws in a little bit of EDTA to bind up any of the free metals coming off of the aluminum can, so it doesn't taste quite so metallic, because you've removed all of the extra ions. So one of the things I'll encourage you to do sometime is grab a random food or drink product off the shelf and look for EDTA. It will show up way more places than you think, because it is very good at binding these species. However, they also end up playing a really key role in a lot of other activities, such as biology. If you have, say, too much toxic metal in your body, you often end up getting extra EDTA to help your kidney function remove these toxic metals from your body. But we often see things like other sort of chelating agents and ligands binding to metals to help them move around inside your body so that they can move past things like cell membranes, and as well as change the actual function of these metal centers so that they can do things like catalyze or speed up chemical reactions in your body. Most of the really cool reactions that occur inside your body occur using metals, and they're often supported by some kind of ligand. So next time, we're going to go ahead and look at how we can name some of these more common coordination compounds. Until then, take care.